Hey there, this is Brian Fields. I kind of have an interesting thing here. This is a optical transceiver. Not just any, this is a 2 kilometer 400 gig transceiver. This is known as a QSFP-DD, double density. And this is, interestingly, it is actually implemented as 4 102 with some overhead, or 106 with some overhead, something like that. But essentially 4 parallel streams on the same fiber in different frequency ranges. They're close. It's all what's known as 1310 nanometer optics. However, they use discrete wavelengths, and they mux them and demux them. And this is kind of neat. I'll zoom in here a little bit. I just thought this was neat to be able to break it down. You can see this is the actual transceiver itself, or the case for it. And if you actually notice here, there's quite a bit of heat sink material on them. And these things do run some power. You can even see here there's a clear transmit and receive side on this. This is the transmit side here. This is the receive side here. And the screws are just going everywhere here. But these actually don't use a ton of power. These are the shorter reach optics. They're still single mode. They're not coherent though. There's some coherent optics that'll use upwards of 25 or 26 watts per optic. And these are pretty small, but I think what's really interesting here is the circuit board itself, and this has some opto parts to it and some electronic parts. First and foremost, one of the things that's just perhaps the most interesting to me is the circuit board itself. And if you can see over here, these are individual pads, and this is repeated on the other side as well. What's neat is you'll notice there's no vias or anything. These are actually vias on the other side of the pad. I believe, you'll see we notched the side of this trying to look at it. This is somewhere around a 12 or perhaps 14 layer board. The way these things are stacked together, I'm not going to go into, but it is an interesting manufacturing process that goes into this, because the digital signals here are so fast, and keep in mind they're done in with differential signaling. So each transmit bit stream that's 100 gig requires 2 pairs, or excuse me, a pair of pads. So that means you're using 8 wires essentially for transmit, because there's 4 parallel transmissions, and then another 8 for receive. So it gets to be quite a bit. And if you'll see here, there's a bunch of housekeeping stuff. I'm not going to go into all the bits and bobs on here. But the main thing is, since these use what's called a PAM4 modulation, or 4 different amplitude variations along the fiber. Most other fiber prior to PAM modulation is something called NRZ, or non-return to zero. Very, very similar to what Ethernet uses, because it is Ethernet, but it's a very popular way of doing it. However, it's either on or off, essentially. This allows you to pack more bits per transition. But this device here, this is the main DSP driver chip. And you'll see it's going in here and hitting, these are the receivers here. So this is coming off the receive side. And if you notice, this actually looks like there's a lot going on here. This is optical prisms and things like that. The way this normally works is from the factory. I had to pry this off. There's this little metal thing that goes over it to kind of shield it from light, essentially. I'm assuming for testing and whatnot, protect what's in there, because this is open like this. There's there's no fiber coming directly out of this. And you can see here's your connector right here that you would plug into. And of course, there's this little protection here. These are the transmitters here, and you'll see there's 4 of them. Then it goes through this thing here that kind of culminates them all together. And then there's nothing there except, focus here, let's see, this thing right here, and that's your transmit frequency prism coupler thing that keeps all your stuff separate. Actually, is that transmit or receive? I think that's, let's see, this goes in there like that, so this side here, I'm sorry, that's the receive side. Well, no, be in here like this, so this, yeah, okay. This is receive, this is transmit. That's what I thought it was. And so here's your essentially frequency splitter here that splits all these different wavelengths into what the system can see. Now, it's all infrared radiation essentially, and you can kind of see the same thing here coming on your receive port. There was a piece in the middle there, right in the center. You can see where I kind of busted that out. But it was a very similar sort of a thing. And it's kind of wild that this stuff is actually just, open to the air, or, open to the atmosphere inside the pluggable logic itself, pluggable module itself, between that and the receiver side here. And I'll pull this out. I took this off so you can see that. Let me pick this up here. Okay. You can see the transmitter here. There's a prism that got cracked on there, but these are the actual individual lasers themselves, and there's 4 of them, one for each different wavelength on here. And these all get split together, or split apart, whatever you want to say, and go through the combiner there. And the same thing happens on receive. So this is how it splits this into separate frequencies. And then this here is your receiver. And you can see there's quite a bit of optical stuff going on there on the receive side. The receive's probably a little more harder to do because you have to have a prism that splits all this stuff up into its different frequency components and has, each frequency hit the right, pin photodiode that's under there. And that gold thing, of course, is your photodiode. And then, there's your transceiver chip. That's what does your FEC and your PAM. Various other parts for management. There's an EEPROM on here. And then, this is all station keeping stuff, I think. Well, there's some sort of an atmill there. There's a oscillator for everything, and then a bunch of power stuff. So, but again, that is a wild way that they do this, and you'll see how thick this board is. It's actually very thin. However, there is definitely a ton of layers in it. And you see it's got the exact same thing here on the other side. So this is a double-sided contact with a bunch of buried vias on it. So it's just wildly dense. I like it. But one of the cool things I want to show, because you still have these parts here, is you can actually see how these are frequency selective. And I have a little VFL, which is a much, much higher frequency. But what you'll see is, here you have 4 different frequencies here. You will see when you actually put light into this, the majority of it will go out one of them because it's it's a high pass and a low pass filter, and then 2 band pass filters essentially, or that's how it works here. And the majority of the light will go out one that's frequency selective. So let me show that. I don't know how well that'll show up on here, but it's kind of neat. So I have my, my fiber here. And let me turn this on. Okay, so it's definitely not going to show up on camera very well. that's not going to work. You can see the light coming in here, and this is a much higher frequency because it's visible red. But if you look here, I don't know if you can see that, but essentially the majority of it, I think this is pretty good. You'll see how there's the 4 different outputs there. And the majority of it is going through the lower output. And you can see where it's actually shifting on my hand here because of that. And because it's a lower frequency of light, or higher frequency of light. So this would be your high side, because this is much higher. It's a narrow wavelength, higher frequency of light than this would normally be operating at, which is 1310 nanometers. This is like 800 and something nanometers for these little red lights. But I thought that's just pretty damn cool that it's a bit of passive physics happening inside these transceivers as well. You can see if I do the same thing on the actual receive side here. What that does is it spreads it out quite a bit. And then that goes into, of course, this part here. And actually, I might need to line this up here. Give me 1 second. Okay, so that would be like that. And I don't know if it's obvious there, but you can see the majority of the light is going in one direction here, because this entire part here is the receiver, and the majority of the light is going only into one of the receive photodiodes. So it's definitely showing the frequency selective portion of it. So anyways, I thought it was kind of a cool thing. I mean, this is completely dead. Let me turn this off. And, it's no great mystery what happens inside these things, but to, I think, most network people, they've never seen one of these. They've never had the opportunity to pull one apart. And, it's when you have something that's dead, yeah, pull it apart, because there's a lot of physics and a lot of cool stuff that happens in here. So, anyways, I hope you all enjoyed this, and, feel free to, when you have dead optics, rip them apart, see what's going on. When you get into the coherent optics, which are the DWDM optics that can go great distances, things like that, this is just kind of standard, fairly cheap optics at this point. Those are a lot more complicated inside and have a little bit more going on. They make some optics that'll break out in like 10 by 10, and they have all kinds of stuff in them that's, I don't have any of those that are dead. Otherwise, I'd gladly rip one of those open. So anyways, hope you enjoyed all this, and let me know if you have any questions in the comments.